Alrighty, everybody. I just got the okay to start the show, so we're going to shift gears real quick. I want to put away our space trivia questions on screen because now we're going to be transitioning into the unknown. Ooh. And once again, everybody, welcome to the Morrison Planetarium. I just want to introduce myself real quick. My name is Christian. I'm going to be your planetarium presenter for this show. And just a heads up, I'm at the pilot's booth right behind you, if you're curious where my voice is coming from. Hey, good afternoon, everybody. But don't hurt your necks. Look forward into the dome before you. That's where the whole show is going to be. Everything that you see in purple light is going to be one enormous screen, thanks to the help of 6 different projectors hiding throughout our planetarium dome, which is going to give us a very immersive experience. And just to let you know, folks, the show that we're doing here is different from all the other shows that we've done in the Morrison Planetarium today. This show is called Tour of the Universe. Essentially, what this means is that you're going to hear my voice for the next 30 minutes or so, and we're going to start off pretty close to Earth, and we're going to zoom all the way out to the very edge of the known universe. Hopefully, by the end of this show, you won't have an existential crisis of where we are in the universe because we are very tiny. And before we begin, I got to go over some quick house rules just so that we're all on the same page. We can have a great experience inside the planetarium today. First off, there is no food or drinks allowed inside. So if you manage to bring any snacks or beverages, make sure those are tucked away till the very end of the show. We want to keep this planetarium nice and clean. This also goes for no feetsies on the seatsies. So again, please have your feet on the seats or off the seats on the floor because again, we want to make sure that our planetarium stays clean. So thank you, y'all, for your help. And also, folks, please, once again, wear your mask throughout the entirety of the show. We've got about 80 people in this planetarium right now. So again, we're going to be in here for about 30 minutes. So please wear your mask, even during the dark portions of the show. I can't stress that enough. Thank you so much for your help, y'all. I really appreciate it. And also, folks, if you happen to have any 21st century gadgets like cell phones, smartwatches, tablets, beepers, if you still got them, now's the perfect time to turn them off, deactivate them, set them to stun, do whatever you need to make sure these devices don't come out for the next 30 minutes out of your pockets because they produce really bright white light and they can be distracting for the folks sitting behind you. So again, remember to put those 21st century gadgets away, any electronic devices. And also, folks, you're more than welcome to exit at any moment during the show. All we ask is that if you do leave, please make your way up the stairs. That's where the exits are going to be located before, during, and after the show. It's much easier to climb the stairs in the dark as opposed to walking down them where you can easily trip and fall in the dark. Trust me, I know, I have bruises. They really hurt. So make sure to make your way up the stairs, not down them to exit. And also, folks, this show is quite immersive. If at any moment during the show becomes too overwhelming, you become motion sensitive, there's a really quick and easy solution for you. All you got to do is close your eyes, take a few moments to take a big, deep breath, and your brain will remember that you're sitting in the planetarium in San Francisco and not hurtling through space, at least not more than the usual. But otherwise, it looks like we're ready to go. We're just going to wait for the last few cell phones to be put away, and then we'll begin. Alrighty, everybody. Looks like we're ready to go, so let's get started. Alrighty, once again, folks, as I mentioned, we're starting off pretty close to home, but this doesn't really look like home from this perspective. That's because we are starting off at the International Space Station, or what we like to call the ISS. And you can see down below us that big circle, that is planet Earth, so not too far away from planet Earth. But I want to talk more about the International Space Station because this thing is an amazing feat by humans. So the International Space Station is essentially a research facility that's orbiting around planet Earth. And many countries around planet Earth came together to pretty much figure out what happens to things in space. For example, how do plants grow out in space in a low gravitational environment? How do humans react to living out here in a vacuum of space or a low gravitational environment? Does it change the human body at all? How does fire react out here? Does it behave the same way as it does on Earth with gravity? And same thing goes with water. So all different types of experiments, science experiments are conducted here on the International Space Station, which is by far my favorite research facility around our planet Earth. So really cool. But not only that, folks, From here, it looks like the International Space Station is like 1,000,000 miles away from the Earth, but it's not that far. It's actually relatively close to the Earth. It's only about 250 miles above the surface of the Earth. So 250 miles, that's like a nice little family vacation from San Francisco to Santa Barbara, a nice little getaway weekend with the family. And folks, the International Space Station is going incredibly fast. It's going a whopping 17,000 miles per hour, where it orbits once around the Earth every 90 minutes, and it experiences 16 sunsets and 16 sunrises a day. Woo, how romantic. And folks, the International Space Station is as far as we put humans into space nowadays, because traveling into space gets quite costly. First off, you got to get yourself a rocket ship. Either you buy it or you make your own rocket ship. And then you got to get yourself rocket fuel to get that rocket ship off the planet. And then you're going to need more rocket fuel to get that rocket fuel off the planet, and more rocket fuel for that rocket fuel to lift the rocket. And then you got to get more rocket fuel, and you're going to need more rocket fuel. And then you're going to need to bring all the water, the food, and the air you're going to be breathing while you're out here. So it gets quite costly quite rapidly. So again, this is as far as we put humans into space nowadays. So only 250 miles above the surface of the Earth. And folks, the International Space Station is about the size of a football field, give or take, although it keeps getting bigger every year because they keep adding new modules, new compartments to it. So it keeps getting bigger. But for now, we're going to leave the International Space Station behind because this is Toward the Universe. We want to figure out where we are in the universe. So we're going to depart away from the International Space Station, and we're going to see it slowly disappear compared to our planet Earth. Now, to make sure that we don't lose track of the International Space Station, I'm going to put the trajectory there, this nice little orange line, so we can keep track of where it is as we start to zoom away from planet Earth. And just to let everybody know, we are using a different software than the previous shows that we have before. We're using a new space software called OpenSpace. Now, just to let you know, this program is in its beta stage, which means it's not completely finished, which means that we might run into a glitch here and there, but that's totally okay. I'll point them out if we happen to run into them. But what's really amazing about OpenSpace is that it pulls data from geo satellites. So when we're looking down at the Earth right now, we're looking at the weather patterns, the cloud patterns as it looks like as of yesterday around noon. So OpenSpace pulls from satellites to give us very accurate recent information, which is amazing in my opinion. But we're going to leave the Earth because we're going to be heading over to our nearest natural neighbor to us in space, the Moon. Now, we humans have been to the Moon before, but it's been quite a while. It was between 1969 and 1972, thanks to NASA's 6 Apollo missions that brought a total of 12 incredibly lucky guys to walk on the surface of the Moon, play golf, and of course, conduct science experiments. But the last time was in 1972. That's a little more than 50 years ago or so it's been a little while since we sent humans out here. But don't worry, folks. NASA has a new space mission in the works that will be sending humans again to the Moon in the next year or two, as long as everything goes correctly. And that new space mission is called Artemis. So keep your eyes and ears out for any news about Artemis, because this is going to be a really cool space mission. They're going to be sending the first woman to the Moon. But not only that, they're also going to be pretty much setting up the first lunar base on the Moon. Essentially, the goal from NASA is that they want to send humans to Mars, but in order to send humans to Mars, we need to figure out how we're going to live in a celestial body out here in space. So instead of sending humans 6 to 8 months away from us on a totally different planet and trying to have them figure out how to live out here in space, well, it's much easier for us to figure out how we're going to live out here in space by heading over to the next natural neighbor to us in space, the Moon. So much closer to home, easier to figure out how we humans are going to live out here in space. So again, look out for any news about Artemis. It's in the works right now. I'm very excited to see what happens. But again, folks, we are at the Moon, and here on Earth, when we look up at it and at the night sky, sometimes it feels like you can almost reach out your arms and touch it. It feels so close. But the Moon's incredibly far away. It's about 240,000 miles away from the Earth. 240,000 miles. Some of you folks may own a car with that many miles on it, and if you take better care of your car than I do, you can even imagine driving to the Moon if you drove for 4 months nonstop going 80 miles per hour. Although I cannot recommend it, the roads out here are poorly maintained. Hee hee hee. And folks, from here on now, we're going to need to use a more useful measuring stick, since at this scale, using miles is kind of like using inches to describe the distances between cities. Astronomers instead use a more convenient measurement known as light speed. And light travels at a mind-boggling speed of 187,000 miles per second. In terms of kilometers per second, that's 300,000 kilometers per second. So while it took the astronauts more than 3 days to reach the moon, traveling faster and farther than any human has done so ever since, it only takes light 1.5 seconds to cross that distance at the speed of light. That's kind of like the same amount of time it takes for a short pause in conversation. But now, folks, we're going to leave the moon behind. So everybody say, bye-bye, moon. We'll see you later. And now, folks, we're going to be taking a leap into a much greater realm of our solar system, because we're going to watch the moon and the Earth in its orbit slowly recede. In fact, I want to bring up all the planetary orbits. Whoa, there we go. But now we're going to be traveling much faster than the speed of light on our journey, because we're going to be traveling at the speed of the human imagination, thanks to the help of computer models like OpenSpace, showing us the most accurate images and information available to us. But now the nearest star to us, the sun, comes into view, and the sun's roughly 93 million miles away from the Earth. Whew, 93 million miles away, that's really far away. But in terms of light speed, that's not too far. 93 million miles at the terms of the speed of light is only 8.5 minutes. So 8.5 minutes for that light from the sun to reach us here on Earth. But again, the sun's right in the middle. Earth is the third rock from the sun, a little bit to the right side. So the light emitting from the sun right now takes 8.5 minutes to cross that 93 million miles, and then it reaches us. Now, this is a really cool concept to keep in mind, because, folks, if the sun was to turn off all of a sudden, we humans here on Earth wouldn't know about it for 8.5 minutes, because that light hasn't reached us yet. So if the sun was to turn off all of a sudden, 8.5 minutes of light for it to travel that distance, and then all of a sudden it would be nighttime here on the Earth. Now, this is a really cool concept, because this also works for very far objects. For example, a star that's 2 light years away. So if we're looking at that star 2 light years away, we're looking at that star as it looked like 2 years ago in the past, because it takes that long for that light to reach us here on Earth, for us to observe it. So the further you travel out into space, or look out into space, it's kind of like going back in time. Pretty cool. And before we leave our solar system, I do want to name the planets in our solar system. So right in the middle, we have our sun, Sol. And then the closest planet to the sun, we have Mercury. Then we have Venus, Earth, and Mars. These are the rocky terrestrial planets. This is something that we can send spacecrafts to and land on, although I wouldn't recommend it for a couple of them, because the weather there is quite extreme. And then beyond Mars, we have our main asteroid belt, which looks something like this. Asteroid belts. There you are. So this is our main asteroid belt, folks. This is what it would look like if we were to highlight all those asteroids in our asteroid belts. So a very large number of asteroids here. And then beyond the asteroid belt, we have the really big planets. We have the gas giants. We have the Jovian planets. We have Jupiter, Saturn, Uranus, the funny one, and Neptune. So these are the planets in our solar system. And I can already hear a few folks, hey, Christian, you forgot to add Pluto. What happened to Pluto? I learned about Pluto in school. Tell me more. What happened to Pluto? Well, I can add Pluto's orbit into the mix, folks. And let's do that right now. And I just brought up Pluto's orbit. It's going to be represented by this fainter blue line. But as we look at it from a sideways perspective, you're going to notice that Pluto's orbit is different from all the other objects I just mentioned. Pluto is on its own eccentric orbit tilt. So it's not like all the other objects I just mentioned. And folks, just to let you know, Pluto is no longer considered a planet. It's now considered a dwarf planet. And the reason why is because in the mysterious year of 2006, scientists and astronomers got really good about learning about the outer part of our solar system, the region beyond Neptune, so all this stuff beyond here. And what we found was essentially the Kuiper Belt. And you're probably wondering, what's the Kuiper Belt? I've never heard of that. Are you making things up? Well, no, folks. The Kuiper Belt is all this stuff out here. So this is the Kuiper Belt. This is essentially a second asteroid belt beyond the orbit of Neptune, mostly made up of icy asteroids and icy comets. But again, in 2006, we found more than 400 objects out here, and some of them were bigger than Pluto, so we couldn't call all this stuff planets. There was just way too many of it. So all the astronomers and scientists around planet Earth came together to create have a great big meeting. Essentially, they had to figure out what exactly you need to be an object to be considered a planet. Now, one of the criteria to be considered a planet is that you need to be so big and so massive that you push all the other stuff out of your orbital path. And unfortunately for Pluto, it's not the biggest thing in its orbital path. It kind of gets pushed around. And not only that, it dances with its own moon. So Pluto has a moon, and it does like a little dance. It orbits around each other. So not the biggest thing in its orbital path. And this is one of the reasons why Pluto is now considered a dwarf planet, no longer a planet. But don't worry, folks. Pluto's not the only dwarf planet out here. We've got quite a few of them. We've got Make, and Haumea, just to name a couple of them, out here in the Kuiper Belt region. And then, of course, we also have Ceres in the main asteroid belt. But I want to put away the Kuiper Belt because that's just a whole lot to look at. And really quickly, before we leave our solar system, I do want to show you the spacecrafts that we sent out in the 1970s to explore our solar system. There they are. So these are the spacecrafts that we sent out in the 1970s. And essentially what we have here are the trajectories for Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2. And the latest of them, New Horizons, which we can see the orbital path of New Horizons. It's pretty close to Pluto. You can see right over here the orbit of Pluto. And then the closest spacecraft to us right here. So that's New Horizons. Pretty much New Horizons did a quick flyby of Pluto in 2015 and gave us some really amazing high-definition images of Pluto. Before, our pictures of Pluto were pretty much pixelated, and we couldn't really figure out what exactly this object looked like. But thanks to New Horizons, we got some amazing data sets with that quick flyby. But all these spacecraft, folks, are traveling fast enough to escape the gravity of our sun to leave our solar system. But the most fastest, or the most more further, the one that traveled the most furthest, Voyager 1, has not yet traveled as light travels in a single day. Now, in order for light to reach all the way to the orbit of Pluto, it's going to take about 10 light hours to get this distance, so nowhere near close to a day. But now, folks, we're going to be leaving our planetary scale long behind, because now we're going to be heading into interstellar space, the space between the stars. Distance now becomes so immense, it's going to take us about 4 years at the speed of light to reach the next star system to us. And as we leave our solar system, you can see that we are now looking at the true brightness of our sun as it would look like outside of our own solar system. Our solar system becomes one of many stars out here. And if my calculations are correct, folks, the Alpha Centauri system is going to be up here on the top right. So 4 years at the speed of light to reach this distance. That's about the same amount of time for a college education from freshman year to graduation, at least before the budget cuts. Hee hee hee. And folks, we're going to stop to consider whether humanity has made its presence known beyond our solar system, because now we're going to step into something called the radiosphere. So this is the radiosphere, folks. This represents the current limits of the most distant radio signals humanity has ever broadcasted, or rather leaked into space. And it extends about 90 light years in all directions, emitting from the Earth. And this first began in the early 1930s with strong radio waves, early television, radar signal, and then later the detonation of atomic weapons. Now, all these things are emitting electromagnetic radiation strong enough to escape the Earth's ionosphere. Now, humans were broadcasting well before that, but the earliest radio was not quite powerful enough to escape the Earth. Now, since all these signals are electromagnetic, they travel at the speed of light, so this is kind of like humanity's electromagnetic footprint in the universe. And of course, the radiosphere is always expanding at the rate of 1 light year per year, so is anybody out there listening? And folks, right now I'm going to be adding these markers into the mix. These markers represent some of the many thousands of stars astronomers have discovered over the last 22 years, which has one or more planet orbiting around them. We call these planets exoplanets, and we're looking for any of them that are Earth-like with conditions suitable for life as we know it. So far today, we found more than 4,000 exoplanets in our nearby vicinity to us. And that number is going to be constantly growing in the future, folks, because we have space-based telescopes that are just devoted for searching for exoplanets in our nearby vicinity. To figure out if any of these exoplanets are Earth-like with conditions suitable for life, well, that is a different story. But we have new generations of astronomical instruments that are devoted for that search, but we're not quite there yet. But the important point here is that quite a few of these planetary systems are within that 90 light year limit of our radiosphere and could have potentially received our signals. However, since radio waves travel at the speed of light, if there is anybody that's out there that's able to listen in and answer back, the communication delays between hellos could be decades in time. Now, to give you an example, let's say we live in this star system on the far left, right over here, and we find an alien civilization on the other side of the radiosphere. Let's say this one over here. We shoot them a text message, hi. It takes 90 years to get to them. They listen in, answer back, they say hi. Another 90 years. That is a 180-year conversation in the making. Woo, and I can barely wait for a text message from my friend. But of course, folks, planetary systems beyond the radiosphere, more than 90 light years away, have not heard from us yet, but eventually they will, as the radiosphere is always growing, but it becomes weaker as it does. And for now, folks, I'm going to put away our exoplanet markers, but I want to leave our radiosphere up there because this is going to be a great reference point. As huge as this radiosphere is, it is nothing compared to the Milky Way Galaxy. So keep your eyes on that radiosphere. Let's see if you can still see it as we zoom on out. There we go. So now we're looking down at our Milky Way Galaxy, folks. And you notice that we live on the outskirts of our Milky Way Galaxy. So we kind of live in the suburbs, if you would. But our Milky Way is incredibly large, folks. If you wanted to cross our Milky Way from one side to the other, well, it's going to take you 130,000 years at the speed of light. Now, that is a very long road trip. But not only that, folks, our Milky Way is so huge, we estimate that there's at least 300 billion stars in our galaxy alone. If our recent discovery of so many exoplanets within our small neighborhood within this vast star city is any indication, there could be billions of planets and potentially millions of Earth-like planets throughout our single galaxy. And before we leave, I do want to stress the shape of our Milky Way Galaxy. When we look at our Milky Way Galaxy from a sideways perspective, you notice that we live in a flat spiral disk. Now, this is pretty important because when astronomers and scientists want to learn about the universe, it's much, much more easier for them to point their telescopes and equipment galactically north and galactically south instead of looking through the plane of our Milky Way Galaxy, which is filled with stars, planets, gas, debris, nebula, which obscures our view of the universe. So just keep that in mind. Astronomers tend to point their telescopes galactically north and galactically south instead of through all that gas and debris. That'll come up in just a little bit. But folks, our Milky Way is only one of many hundreds of billions of galaxies that comprise our known universe. In this giant leap, we're now about to see a view where each point of light no longer represents a star, but now represents the location of an individual galaxy. Each galaxy containing hundreds of billions, perhaps trillions of stars. Now, we live in a local galaxy group, which contains about 30 galaxies, large and small. It also includes the nearest large spiral to us, the Andromeda Galaxy, only 2 million light years away, just next door, and heading right for us. We're going to get to know it pretty intimately in about 5 billion years, so mark your calendars. And folks, as our picture starts to expand even more, we discover that galaxies are not evenly distributed throughout space. Instead, galaxies tend to clump together in clusters with great clusters. In fact, we can see a really large galaxy cluster on the right-hand side. I believe that's the Virgo cluster. And also, galaxies tend to create voids, regions of space that have very few galaxies. You can start to see very sparse regions where there's not really galaxies in that spot. So we got clusters of galaxies and empty regions or voids. But folks, now we're zoomed so far back now that this picture represents the 30,000 closest galaxies to us in a space over 300 million light years across. Now, we've got to give thanks to a very special fellow by the names of Dr. Brent Tully, who worked at the University of Hawaii, who compiled this amazing galactic map representation from the work of dozens of astronomers along with himself, working over decades of time. And they even color-coded the densest regions of galaxies in orange here on our planetarium dome. But now, folks, we now have automated systems that are mapping even the most distant galaxies. So now we're about to see the large-scale structure of the universe. And here it is, folks. Here is the large scale structure of the universe. And just a heads up, the universe is not shaped like a bow tie, although it kind of looks like it. Remember when I just mentioned to you that we live in a flat spiral disk of our Milky Way galaxy? Well, if we were to line up our Milky Way galaxy, it would be right in these dark regions right there. So it would line up just like that. So again, astronomers tend to point their telescopes galactically north and galactically south instead of looking through all the gas and debris of our Milky Way plane. But astronomers still wanted to make sure that there was galaxies even through the plane of our Milky Way. So we have this nice purple data set right in the middle, and this shows all the galaxies they were able to find by looking through the galaxy plane. Now, it was much more difficult to find these galaxies because, again, all that stuff in its way, in its path. But as our technology progresses and gets better, those dark gaps that will eventually be filled in, it's only a matter of time. And remember, folks, every point of light that we're seeing is an individual galaxy. These are not just stars, these are galaxies. So there is a whole lot of galaxies out here. But, folks, it looks like we're running drastically out of time. So let's continue on to the very edge of the known universe. And now we're going to be zooming so far back now, folks, that we're going to be looking at the quasars. So the quasars are going to start to appear. They're going to be represented by these nice dark orange dots at the very edge of our large-scale structure of the universe. You can see a lot of them on the right-hand side. Now, with the quasars, we're viewing the brilliant core as the central nuclei of very young, very distant galaxies. Again, these are known as the quasars, which are short for quasi-stellar radio sources. And these blazing objects are all billions of light years away. So now we're looking so far back in the depth of time and space that the most distant quasars represent the universe at a much earlier age. We're nearing the very beginning of galaxy formation. In other words, with the quasars, we're viewing a sort of awkward, gawky teenage version of the universe. And before there was a teenager, there was a baby. So now we're going to press even much further back before a time before quasars, before planets, stars, and even galaxies began to form. Folks, we are now about to approach the very edge of the known universe. We also call this the cosmic microwave background image. There we go. So this is the cosmic microwave background image. We also call this the CMB image. Now, all evidence indicates that the universe we live in is about 13.8 billion years old. And this is data compiled by Planck and other radio telescopes. And this is a picture of a very baby universe, only 380,000 years after the Big Bang occurred, where space and time began. And what we're looking at is not a typical photo, but a temperature density image, where the light echoes of the Big Bang are color-coded, where the lighter areas correspond to the hottest, least dense regions, and the darker areas, the coolest, densest regions. These fluctuations in temperature and density are extremely, extremely tiny. They vary no more than 1 part per 100,000. But eventually, they gave rise to that large-scale structure of the universe that we saw moments ago, that clumping and clustering of galaxies everywhere. Figuring out just how that happened is one of the larger challenges for cosmological research today. Though our view here is of the outer edge of the known universe, the earliest light visible to us, that radiation actually persists all around us. It permeates the universe, stretching and cooling as the universe expands over billions of years of time. But folks, this is as far back as the law of physics can physically allow us, so we only have one direction left to go, back home. Now, before we make our return trip back to planet Earth, I've got to ask y'all to prepare yourself because this could possibly be the worst free-falling dream ever. We're at the very edge of the universe. But let's find a nice entry point through all these quasars and galaxies, and let's begin our return trip back home, folks. Alrighty, folks. So we're crossing the expanse of 13 billion years. Now, we present you with this view of our universe and the latest in cosmological and astronomical information. We're covering eons and observing objects billions of light years apart. Now, we live in a golden age of astronomy with new generations of telescopes and spacecrafts that are extending the reaches of our eyes and preparing for the eventual race between the advancement of technology and the accelerating expansion of the universe. With that thought, I want to remind you all that astronomy is for everyone. You don't need to be a rocket scientist to enjoy the beauties and wonders of our universe. All you need is the night sky, and if you can, get away from the lights of our cities and look up. Even a good pair of binoculars makes for a decent first telescope, and there's astronomy clubs all around the world that invite people just like you to look through their telescopes and peer into the great beyond, allowing you to partake in the wonders that our universe has to offer. Now, astronomy as a hobby can offer an endless supply of satisfaction, folks, and I do hope you'll join us, those who dream amongst the stars. But right now, it looks like we're entering back into our Milky Way Galaxy, our small region out here in one of the arms And of course, we're approaching humanity's magnetic footprint in the universe, the radiosphere. And of course, folks, we are making our way downtown, walking fast, faces passing, we're homebound. And now we're approaching our star system, our planetary systems. We're passing the spacecrafts that were exploring our solar system in the 1970s, passing the Kuiper Belt and the orbit of Pluto. And of course, we're making our way to the third rock from the sun, our homeworld, our little slice of home out here in the universe. The only place humans have ever called home, planet Earth. And folks, as we make our final approach back to planet Earth, this is going to be the end of our Tour of the Universe show. And I want to thank you all for stopping by and watching it with me today. I hope you did enjoy it. But otherwise, it looks like we made it back to planet Earth safe and sound. And that's all I have for you today, folks. Thank you for stopping by. I hope you have a good day.